welcome everyone. Hope you had a nice break. So I'm very pleased to introduce Chang Zhang to every one of you. So she's a principal researcher in Microsoft Research Cambridge. She works in a few things. One of those is causality, and we're very pleased with having her in the workshop here today. So as we have done before, you can ask your questions in the chat, in the Q&A, both in the Zoom and in the Wova app, and we will be checking them and moderating. In this case, Ribo is going to be doing that. So I leave you with Chan.
Thank you very much for the introduction, and thank you all again for organizing such a fantastic workshop and inviting me to share some of my research idea here. And also, as Javier said, Ribo is here, so he will be like operating kind of as operator and TA at the same time, because I just want to make sure all the questions get answered, and I may run out of time for that. So Ribo will type in the chat window directly to answer some of the questions, and for the typical questions, I'll have breaks in between so that Ribo will read out and we can have more discussion as well. I see a raised hand, so is this Javier? Do we have question in between or something?
I don't think we have any questions yet. But before you start, I just wanted to mention that we are going to record the talk if you're okay with that.
Okay, sure, no problem.
Yeah, I think we can go ahead.
Okay, great. So, morning everyone. So today I'll talk a little bit about causal discovery. But I'll cover a couple of things. First, I'll go a little bit with the methodology. I'll have a very quick overview of the methods for causal discovery, and I'll talk about one of our contributions, which is causal discovery in the presence of missing data. I'll briefly go through how to evaluate causal discovery algorithm, and in the end, as we're all machine learning researchers, and I want to make a small connection on how the result from causal discovery can also be used in other machine learning applications and bridge the gap from causality to other machine learning directions. So very glad to be here today. Okay, so I think we all know by far it's super important to understand causal relationship. Is in a medical setting, the medical doctors need to know how to treat a patient, because what they actually need to know is not like a prediction. They want to know whether a medicine A will make the patient healthier or medicine B will make the patient healthier. So if they don't, if something is, for example, the patient is more sicker and given medicine A or something, that can be correlation, but not causal relationship. To really improve the patient health, the causal relationship is needed. The same as, like, for example, for shops or entertainment park, how to treat customer, like what they really care is what they can do for customer so that the customer can be happier and enjoy their product more or enjoy their experience more. So it's super important in many real life applications that to understand the causal relationship. So it has been taken as almost the golden standard for randomized control trial, and that's been working perfectly fine for many scenarios. But as you can imagine, there are many scenarios we cannot just take randomized control trial as well for ethical reason or any other restrictions. Even for a basic topic such as whether smoking causes cancer or not, we cannot just take randomized controlled trial and take a group of people and ask these people to smoke, because it's not ethical, it's not moral, and maybe this is really harmful for a person's health. So similar situation exists in many scenarios in real life, and it can have very difficulty to really carry out a randomized control trial. So what we need to do here is probably we need to do causal discovery from whatever data we have. Like it can be observational data or experimental data, but it's not randomized control trial data. So the task here for causal discovery from observational data is you commonly have a data set that may look like a tabular data. On the left, the variables A, B, C, D can be anything. It can be like age, gender, C can be, for example, the chance to get for a certain lung disease or something. So these are different variables. You may have a big data set and you have many data, and then they take different value. So what you care about is, with this given data, how can you find the causal relationship? And then you want to discover something what I show on the right. That's a causal graph, which means that you care about whether A cause B or A cause C, what's the relationship between them. So that's the task. Hope this is clear. And with this task, like discovering causal relationship from observational data, how can we do it? So traditionally, there have been many methods developed in this direction. It's an extremely exciting research direction and has a long history. There are many ways to group the methods together, and I'm presenting one of the most common way to view these methods together. So there is no hard boundary between these methods. This can be combined as well, but I'll just take one of the most popular view and briefly introduce like what are the three types of methods like commonly used for causal discovery from observational data.
Sorry, Chen. Sorry to interrupt you. It seems like there is a sidebar in your screen.
This one.
Yeah, it seems like there's something on your screen when you share your screen. Yeah, now it's better. Good. Now it's good. Yeah.
Great, thank you very much. Now hopefully everyone can see it. Okay, great. So as I said, there are three types of methods. I'll just give a very brief overview of them. So these methods are functional causal models, score-based methods, and constraint-based methods. So for functional causal models, so what are they? So we think there is a functional relationship. There is always a true underlying generative process that follows the causal process. So we say there is an effect of y. It is a function of its direct causes x, and the theta here is a parameter of this function, and some noise variable epsilon here. And so for this way, so the variable x and the noise epsilon, they should be independent from each other. So if we assume we can find such a function, and there must be only one way we can have the noise independent from the x. And then if we fix the function in the wrong way, so the noise and x won't be independent. So that's the high level idea, because to find a function that enable that the noise and your input variable are completely independent. So let's just take a very simple example. Let's think about just a 1D scenario, and let's think about one of the most famous methods that is actually called LINGAM. It's linear non-Gaussian model. Let's look at the second row of this picture. So what does functional causal model mean? Like, what's the idea behind it? It is, think about if there is actually y is the effect, x is the cause. So if that's the real underlying generative process, and your observation may look like this. Let's assume the noise is uniform random. So this is your observational data, like x or y. I mean, you can put it in any way. So that's you have a data set that is observational. So if you're trying to do regression, you assume it's a linear model. You do a linear regression, and you're trying to do a linear regression, try to fit like a y equals bx plus epsilon. If you fit this data in this way, where x is input, y is the target, you'll fit in this way, and then you will have your epsilon. You can plot out your epsilon and x, and in this way, you see epsilon and x are independent for the same data. And if we want to do the regression the other way around, if we want to fit a model, that is x equals the parameter by multiplied by y plus the noise. You'll do the same linear regression procedure on this picture. Can you see my cursor? Ribo, can you see my cursor?
Yeah, we can see it, yes.
Okay, great. And so if you do the linear regression in the other way, you still can fit the data pretty well, but then you also get your epsilon. And if you plot out your epsilon and y, because in this case, you're assuming y is the cause, x is the effect, and you'll see this one. You see the epsilon and y are not independent anymore. So this is the idea of a functional causal model. You assume a functional form, in this case, a linear model, and then you can fit the variable in two ways, assuming one is cause, one is effect, and only one is the correct causal direction. The noise term and your variable the one you assume is a cause will be independent. The other way it will not. So that in this way, you can identify whether X cause Y or Y cause X. So why this is linear non-Gaussian model? Because actually there's one is linear model. We always need to make some assumptions. So once linear model, if the noise is actually Gaussian, you will not be able to identify it. The first row shows it. So actually for this type of relationship, there are many extensions. So the only case that you can actually not identify is one is a linear model and Gaussian. And the famous model is Lingam, what we talk about. There are many generations. So the example I showed here is one-dimensional case. It's a toy example. The principle applies in other scenario. So you can generalize it to there if there's many variables, and there's a method called ICA Lingam. You can check the paper. So that can do exactly the same thing, but very efficient with many variables. And there are many ways to extend the function as well. So maybe we don't want to have a linear model because for real generation process, that can be nonlinear model. So there are also methods that assume nonlinear model, and these are called PNL. So it's post-nonlinear model. And then you assume a form like this. It can be, this is nonlinear function on F, and there is a nonlinear function outside, so that can handle very generic case, but the principle behind is the same. There is only when the correct cause and effect were taken into account, the noise and your variable can be independent. So that's the idea behind the functional causal models. And then let's look at the second type of model, that is score-based model. So the idea is extremely simple as well, because recall our task, we have a table of observational data. And what's our goal is to find a causal model that actually explain the table you actually observed. So the score-based model, just the idea is very simple, is you can just loop over all possible graphs because you can have all the graph drew by hand, you know all the possibilities, and you have some criteria, and you think about which model actually explains your data best, and then that's the underlying causal model. And such criteria can be many ways to define it. And the most like a classic way to define it just to use some score like a BIC we are familiar with, and search over all these different combinations and take the best way. And this type of score-based method, like this type of model, like one of the most famous one is called the greedy equivalent search, and that's called the GES. So if you see GES, that just means, okay, we compute the score with different causal graph, explain the data, and take the one that best explains the data. And the last one actually is one of the most popular one in causal discovery, at least for classic causal discovery, is constraint-based method. So the most famous two models under the constraint-based methods are called PC and FCI. So PC was named after the authors, Peter and Clark, and FCI means fast causal inference. So what's the idea of constraint-based causal discovery? So because you think about when you search over all the causal graph, it's a super exponential number of graphs. That is not very scalable. But if we do constraint-based, how do we do it? So we assume, let's say we have 4 variables we want to know the relationship about. We assume they're all fully connected in the first place. And what do we do next is we aim to find the skeleton before we find what's the direction of the causal relationship. We first find out whether there is causal association between variables. And this is done by doing conditional independence tests. For example, if we care about whether there is a causal association between A and D, we condition on other variables and see whether A and D is independent. If condition on any other variables that A and D are independent, we can remove the edge. So we just do this conditional independence test. So as far as it's independent, we can remove it. We don't need to do further, right? So you can condition on many variables here, but if you already condition on C, that's independent, you don't need to try condition on B. But if it's not, we try to condition on B. So you know the computation is faster because commonly the edge is removed pretty fast. And then after you do among all these pairs conditional on all other variables and a subset of variables, you can get the skeleton. So you you get the causal association without knowing what's the direction. And after you know the skeleton, there is actually some rule from PC that can tell you how to find the direction. And this step is called edge orientation. So there are actually very two simple rules in PC. That is, if you find, let's say, ABC, such a relationship, and you know there's A and B, between A and B, there is no edge. If C is not the variable that to remove this edge, which means if given C, A and B will be dependent, so we cannot have the independence, which then in this way, it must be such a V structure. Because given C and B will be dependent, that's the case. And after you orientate this one, and if you have another 3 variable like A, C, and D, so that's in the string. So if this edge is oriented in this way, and this edge will be following the same, the C and D direction. So these are the simple rules of PC-based method. FCI is just another algorithm. They have different rule and they are associated with different assumptions. So all these causal discovery methods have its own assumption behind. And a lot of research effort also goes into how to relax these assumptions. I will not go into the detail of this, but this is the idea of constraint-based method. They differ by their assumptions, they differ by their rules, but the idea is always we try to remove the edge by some constraint, this as a constraint, and then we orientate the directions. So this is a very quick overview of causal discovery methods, and these are the high-level 3 types of methods: functional causal models, score-based method, constraint-based methods, and I mentioned a couple of the most popular and typical algorithms under these methods, including Lingam and IC Lingam. And for the score-based, it's the GES. For the constraint-based, it's the PC and FCI. So if you're interested in this field, it's very exciting. There are many active research ongoing. There are some tutorials you can go through. Like the first one, there is a not too long paper, a very recent review on the causal discovery methods by Peter and Clark actually is here is Peter and Clark by Kuhn, Peter and Clark. And then you can get a quick overview of this field. There are 3 textbooks. If you are interested, you can also learn more about it. I think especially for this one, causal prediction and search, they're much more focused on the causal discovery. Okay, so I'll just take a very quick pause. Is there any questions for this part? Or maybe we will answer all of them.
Yeah, I'm trying to answer one. So one is asking how to check whether 2 variables are independent, because you mentioned we need to do the conditional independent test. Yeah.
Okay, so one more comment on that. For the constraint-based method, for the PC and this type of method, it does not work for only 2 variables, because it's requiring conditional independence tests and all these orientation rules. That only works when the rule involves 3 variables. So for constraint-based method, does not work between only 2 variables, but functional causal models, as I showed before, work with 2 variables.
Yeah, and for another question, I think I can answer in the in the chat. Yeah.
Cool, great. And then I'll go forward. And so I had an overview of the causal discovery, but when I work with data, the data are never perfect. A data set we got, like let's think about a healthcare data set. We may have a patient A, like a very nice gentleman, and he did medical test A, C, D, and E. So maybe this means like a blood test, CT, like for example, urine test or oral test or something like that. And another nice lady, and she only have medical record for the test A and B, and another young girl who only had the test A, B, and D. So the real data we get commonly have a lot of missing observations, and we still need to do causal discovery from this observational data that is partially observed. And the case we commonly face, there are many variables. So how do we do that? Is actually together with Ribo and Kuhn, we contribute based on the causal discovery method, like the constraint-based method, to a new algorithm that to handle missing data. I'll just briefly talk about how did we do causal discovery in the presence of missing data. So why do we care about this scenario? So first, there are missing data, but does it really have a big impact? It does. So in 1920s, there is actually a study and want to find the causal relationship between gender, IQ, etc. So the conclusion is female are smarter. And it's a great conclusion, and it may be very true, and I hope it's true, but sadly, it's probably not. And we need to be careful with it. What's the reason? Is because the data collected there actually they are collected for the people who are actually in the college already. So for the students who are not in the college, we don't have the data for that. And if they only do the causal discovery based on the data that is in the college, so it's more the reason at that time, it's harder for female getting into the college than male getting into the college. And then with such data with missing entries, you may actually get to the wrong conclusion that is very wrong. I hope it was true, but it was actually not true. And so we need to be careful with that, because with this wrong conclusions in medical setting, and you may give extremely wrong treatment to patients, and then that does not help them to improve their health situation and everything. So let's just think about like what happened actually for this. When there's missing data, what people generally do before, and why do we need to be careful about it? So the most simple solution, so for this part of talk, I'll just use PC as the exemplar here. So there are dilation-based PC. So if your data looks like that, you have the table. I mean, you can think about this IQ or like medical tests or different variables. You have missing entries. And then to be able to do the test, you can just delete all these rows where there's missing data. And then you get a new nice table, also with less rows, but you still have all the data observed. And with this new data set, you can do exactly the same thing as there's no missing data and run your PC algorithm again. And then it is not very data efficient. An alternative way is, remember when we do the conditional independent test, for example, we want to test whether C is independent from D given A, and we actually only involve C, D, and A. So instead of deleting everything as far as there is a missing entry, so when we do this test, we only remove the rows where there are missing value in these variables that we care, so that we have more data to test it. So if you test another thing, for example, A, B condition on C, or you only need to, in this case, the same. So for example, A and D condition on C, then you also only need to remove the rows that have missing value. With this variable, you're actually doing the test. So this is more data efficient, but the same principle. So when you need complete data, just remove the rows where there are missing data entries. But this method is exactly the problem that leads to the problem I talked about, because it's the same thing. We kind of deleted the data where female was not in university, and that will give us the wrong conclusion. So before I get a little bit more into our contribution on how it can be wrong, I'll just give a little bit short recap on regarding the missing data and causal discovery. So in this case, one of the common tools we used in the causal graph, when we have missing data, we commonly introduce the missingness indicator. So we call it missingness graph. So when this indicator is 0, it's the most common use case. It means observed. When it's 1, it means missing. And this is a little bit different from other graphing models. So commonly, when a variable have missing data, we kind of shade it in gray. So in this case, it's causal graph. Y have missing data, and here is the indicator of this variable Y. And then also in missing data, there are 3 different missingness mechanisms that you can think about from causal. So there are the 3 missingness mechanisms, MCAR, which stand for missing completely at random, MAR stands for missing at random, and MNAR means missing not at random. So missing completely at random, it means like whether this data is missing or not is like a coin toss. It's completely at random. It's not caused by anything. It's yeah, it just, for example, it's completely random event. You have a coin, and then one something is missing, one 0 is not missing. So that's called missing completely at random. Commonly, this is a most easy case because it doesn't introduce any bias to the data. And what's the definition of missing at random? Actually, at first I find it's very confusing because it's not so random. So missing at random means, so you see this missingness indicator. So the cause for this missingness, this cause is fully observed. So when we know the cause for the missingness, this is called missing at random. So for example, this can be the college. When someone is in the university, this can be the IQ. The IQ is observed when someone is not in the university. The IQ is not observed. It can also be other scenario. For example, this in questionnaire scenario, for example, when someone's is, for example, older, then it's less likely they will fill in the, for example, their income. I don't know whether it's true or not, but there are something like if the age may be the cause for whether they answer the question about their income. So this is a case called missing at random. So the cause of the missingness is observed. And for all other cases, it's actually called missing not at random. So in this case, include many cases. For example, the cause for the missingness is partially observed. It can also be not observed. So in general, every scenario that does not fall into these two categories are missing not at random. This is the most difficult case. And so let's, for our work, we'll analysis, we'll pay more attention and want to know how to do causal discovery with missing data. And so we always need to introduce some assumptions. I'll skip the assumption for the basic PC assumption that include like faithfulness and non-confounder in this. So this will be shared. I will not list it there. So what's additional assumption we need to think about here? So first is recoverability assumption that we need. So one is no self-masking. So which means the cause for X is missing or not is not caused by itself. It cannot be, for example, if a person's income is higher than certain threshold, it never fills information or something like that, because such information is missing. It's extremely hard to get any clue about the data and correct the bias. And second assumption is for the recoverability is the indicator is not a cause. So which means that it cannot be the missingness of Y cause the missingness of X, and it cannot be this indicator is a cause of the observation X. So the indicator cannot be cause. So these are standard conditions, recoverability conditions that can be found in the following paper back in 2014. And additionally, we also have a faithful observability assumption. So this assumption just tells you, so the independent relationship, when it's missing or not missing, it holds the same. So if given Z and given RK is not missing, the independent relationship will be the same as it's missing. Okay, so it's in general the same. So the part that is missing and the part that is not missing is consistent, or the part is observed and the real part, if the true data available, is consistent. So this is a digital assumption. So we'll think about what can exactly go wrong. We know there is a case like in the 1920s that the conclusion was wrong, but we want to know what can exactly go wrong. So first, in our paper, we prove something that for this deletion-based method, we can only make a mistake by introducing more edges rather than missing edges. So we never miss anything. So the mistake always just introduce additional non-existing causal relationship. So that is something we prove in the paper. Here is our conclusion. You can check the proofs in the paper. And then when we know, okay, this is the only type of mistake we're going to make. And so how can we know where such mistake can happen? So another finding we actually have in the paper is, so we actually know in which situation such extra edges can appear. So these are the special situation where this is a slider situation, and only when the missingness indicator of the parent is either the common children or the descendant of a common effect. In this case, it will introduce extra wrong causal relationship between the parents. So this is the only structure such extra edge can appear. So that in this way, even with this conclusion, what we do is, even we can use the deletion-based PC, we know which edge we cannot trust it. So that we know other edge, if the return this edge, it can be true. But if there's such structure, and if they return edge between these two variables, maybe as a person, we can do a human post-processing. So we know this is edge we need to pay attention, and that may not be correct. And this is exactly what happens for the university case. Like this can be the gender, and this can be the IQ, and then this can be the whether getting to the college or not. And then the IQ, the observation of IQ and gender was introduced as an additional edge, like they introduced a non-existing causal relationship. Okay, so how to correct it? Then now we already know where the mistake can happen. Of course, we want to do the right thing and how to correct it. So we actually propose a missing value PC. We call it MVPC. So this is a modification of the algorithm. PC, the same step. We do skeleton search, the same as PC. And then the second, so this is overview algorithm. And the second step, we can use what we just talked before to identify the structure where there's potentially wrong edge. We just need to find this V structure. And if there's edge in between, that can be a potential wrong edge. And what we actually need to do next is how can we correct this edge? And after we correct this edge, we can do find the orientation of the edge the same as PC. So here I'll talk about how can we potentially correct the wrong relationship in the specific causal structure. So here I'll just take an example of the AR, that's the picture I showed before, and Y have some missing data. And the missingness Y is caused by W. So here in general, is if W is a bigger value, Y will be missing. So that's the observation. And you introduce an extra variable. Here is the missingness indicator. When it's observed, it's 0. When it's missing, it's 1. And then let's focus on the variable Y and W. So because in this case, you see there is a V structure, and there is a potential we actually make a mistake between X and Y, because this falls into the structure we just talked about, that additional wrong edge can be introduced. And think about how we actually high level can correct it. And you think about, we can think about our data, maybe there are some underlying distribution, they have some relationship transformation, and then we have some observation of this data, like this can be this point, this data can be this point, this data can be this point, right? So these are the rows, then you can observe these values for both X and for both Y variable and W variable, and they are corresponding to different rows here. And then there are some variable that Y is missing. So these are somehow gone. And we only have the W here, because when W is a high number, these variables are gone. So these are the data we have. And if we only do the causal discovery based on this part, we'll have a problem, because this will introduce additional relationship between Y and X, because we need to delete everything here and delete the corresponding part of other variables. And so what we can do is, luckily, we have this part of data that we know these are rows, right? So the idea is very simple. So we can learn the functional relationship from, like, how to predict the Y from W, right? Because we know the matching relationship. And if with this data, if we can learn a predictor to predict Y from W, we can use this predictor to predict this missing data. So we can fill it using this part of W data, right? So we can do it in many ways. You can just predict in this way. You can resample W. We know when we fit this, we know the noise variable. This is supposed to be independent. We can just resample it and reuse it. So there are many practical implementation alternatives that can all valid. But the high level idea is, if we know this can be the potential case, and we can use the common child which is fully observed to predict it. And then this is our method. And with this predict method, or you can think about with regenerated method, like we can predict everything here. Then we have a new joint that is unbiased. Then we can apply PC again. Then that will tell us whether this edge actually truly there or not. So this is a high level idea. And actually this is a more principal formulation is if we have such a causal structure, this is a jointed distribution. If we care about the relationship between x, y, and z, we actually introduce. So this is with Missingness bias. We care about the true joint, and we can introduce W here and marginalize out. And why we introduce W here is we can factorize in this way, and because of the with W, we can introduce R because given W, this R and this part are independent. So we can do this step. And with this, we can do the prediction and then get a new joint distribution. So that's the procedure. So these are the learning from them. So we introduce the W here. We can learn a new model predictor based on the W. And then with the W, we can generate a new data set. And then we can do the causal discovery on this generated data set that is unbiased. So that's so for the detail, you can also check the paper. So in the paper, there's a lot of experiments. These are synthetic data, so we have different sample size, and here means the error. So this is structural Hamming distance. So it kind of tells us how the error. So the lower the better. And the ideal means if we have the full data set, target means we have fully observed data set, but the same size as the missing data. And the pink bar is our algorithm. And then this two pattern means two different dilation-based methods. So you can see that we are very close to the ideal case as the method can correct and remove these wrong edges in between. And that is much better than the dilation-based methods. And the same, we applied the same method for some more real-world data, and there are some score, like there are some rules because we only know a couple of them, and then we can see that our method is better than the baselines. And we actually work with some medical doctor in Karolinska Hospital at the time. So what they care about, they have a big data set, they have all the patients with sports injury. So these are very typical cases and actually cost a lot and very expensive for famous athletes. And so we use a huge data set that have more than 100 variables and did the causal discovery. I'm not presenting the whole graph because it's very big. So first, there are some causal relationships we find. These are consistent with medical findings. They have medical study about it. And there are some part actually when we present this graph to the medical doctors, they're super excited because they say with fascia and this is a score on how well the patient recovers. And they say they actually was thinking fascia is a cause for how well the patient recover. And this is a way means how to close up the wound after the operation. So they got very excited about it. And this is how causally can be useful because this can be used to inspire medical doctor and to have new study and to see whether there is a real causal relationship. But however, for all other causal relationship we discover, there's no way that we can verify whether it's true or not because we have observational data. And why we're doing it because no one knows what's the underlying causal relationship, and that's what medical doctors care about. And so next brings to our question. Actually, if we have a lot of causal discovery method, how can we evaluate which is the most useful one? We can do synthetic data, right? But that have no real world implication. How well it translates. It doesn't carry like a real world data. Bias property, right? And the marginal distribution will be different. And we also don't know whether it will be useful and whether the scale is the same in the real world. And so in this work, we actually generate real world.
Chen, sorry to bother. Before we jump into the next work, would you mind have some question?
Sure. Yeah. Please go ahead.
I think there are some questions. The first one, I think that this is a good question. Like, can the missingness be diagnosed from the results of standard causal discovery algorithms? For example, lower likelihood of estimating model given the data.
So I think that's a very big question, and I think that we need to look at the context of what other model you are talking about. So I have other research on how to fit data and predict the missing data, for example, with probabilistic methods. Like if you look at my work on ADI and PVE, that's part. But that's, I mean, are you talking about score-based method or something? So I think, yeah, I can have a longer discussion with you, maybe offline sometime, because it depends on the model you are talking about, what you are fitting, and the scenario. But in my mind, there's no easy way just to think about a likelihood, look at the number, and say whether the missingness have a problem or detect it.
Very good. And there is another interesting question about deep generative. Is there a relationship between the causal discovery and deep generative models? Because generative model can also handle missing data.
So it's about deep bias, right? So for deep generative model, there's many work on imputing missing data, and many of this work also from, yeah, I also contribute many to this work. But most of this work have the assumption that it's missing at random or missing completely at random. So it cannot be debiasing the situation when it's missing not at random. So we can fuse the missing data, but the bias still exists. And with such data that you impute, then you do the causal discovery, you still have the wrong relationship.
Very good. And I will take another question as the last one. So yeah. How is the imputation method different than iterative imputation method typically used to fill in the missing data?
So for the, it's how to say this, you are talking about mice, right? So like this missing data, like using as a column to fill it in. So these are different applications domains. So this is similar answer to the deep generative model. So when you fill in missing data, what you care is like commonly how well, like generically what you are optimizing currently, something is like RMSE or something. So how well you fill the missing data and whether you really can debias the data set. That's two orthogonal questions. So that our method on predicting it is we consider the causal structure and with the independent relation through considering the cause of the missingness, so that can actually remove the bias introduced by the missingness for the causal discovery purpose. And for other imputation method, if you think about a lot of methods, like you think of iterative or deep generative model, or even, yeah, there's GAN-based as well, like a GAN and all these models. So they don't consider the same bias. And if the same bias is not removed and there's no proof, I mean, there's also other consideration like how well the model fits and all these things. So you cannot have a theoretical guarantee your imputed data set will recover the correct causal relationship.
Yeah, I think we can continue. I will try to answer the other questions in the chat.
Thank you. Yeah. Okay, great. So I'll just very briefly go through this because we have causal discovery algorithm, but it's hard to evaluate. I just mentioned, so we actually work with medical doctors in neuropathic pain diagnosis because this is the case in real life. In medical settings, people have a real good understanding of it. Let's say this is what neuropathic pain is, of course, discomfort caused by some irritation on the nerve. So there is a clear understood pathological pathway. So commonly this example, if you have disc ligament injury, like for example, if you lift some heavy things, your lower back got twisted, there are some disc ligament injury, that will cause irritation in your nerve. And then in medical setting, you actually have the full nerve map on your body. And for actually, if you hurt your this joint, and it may cause the front part of your leg hurt, or the other joint may cause actually the hamstring part of your leg hurt. So you have the full pattern of the nerve, how the nerve is distributed in the body, and you also know what people can experience as a symptom. Like for example, if the L5 nerve, this is a nerve number because there are different nerve labeled in different way, then it will cause knee pain. And like, for example, the leg pain as well. So we take advantage of such medical setting where the causal relationship is actually known and created the synthetic data set. So the pathology is here. This is example as what I just talked about. There are these causal relationships actually in the tree structure where pathological mean like labels, pattern labels, and symptom labels. And we worked with doctor and actually created this ground truth causal relationship, which have more than 200 variables and 700 causal effect pairs and all different scenarios of these separations. And we actually have patient data from real clinic, and we can estimate all the conditional distribution amount using all the real patient data from medical setting, because they have the doctor diagnosis actually tells you which nerve is irritated. It's called radiculopathy, and also it's caused by which joint problem. And in this way, we create a data set. This is a, I'll accelerate a bit, so I'll just go through it quickly, so that this is a picture. We ask the doctor to evaluate their original data set, how likely this is a real data, comparing with our generated fake data. The higher or the better. Actually, it shows our generated fake data is even a little bit more real than the real data. So this is a blind label study, so that we can generate synthetic data that looks very real. I mean, it's generally the same. So higher number means the patient is more typical, and we have strictly like increasing, like a more typical patient have more as well. And then we also compare like basic statistics. This is correlation, this is on the marginal. These are different symptom label and these variables. And then we can see the real data. This is the data set we have, and simulated data, they exhibits the same pattern. So with such a synthetic data set, then we can do research with such data that reflects a real life scenario, and that can be really useful as well. And then we evaluated many benchmark and many scenario in our work using our simulator. And here just one example is, you can see that this is causal discovery with different sample size, because with synthetic data, we can generate as many examples as possible. And these are like GES, PC, these are the methods we mentioned about, and you can see the causal discovery performance are getting better and better, but even this huge amount of data, the performance is still not satisfactory. So it means that all these methods they have theoretical guarantee on asymptotically correct, but it can be very not sample efficient. So I think that's a good lesson for us, and that also challenges and opportunities in this field. So I'll go up to the, I think this part is very simple. I'll quickly go up to the last part. I'll just show briefly what can causal discovery result can be used for machine learning. I may take a couple of questions in the last minute if it's okay. So now we have the causal discovery result. This is already very useful, because if you give the result to a medical doctor, they can already use this result on like influence their decision on how to treat patients, and like the same for other scenario, like for shops, how they treat their customers. But if with this causal discovery result, can we help other machine learning domains? So this is an example, like I'm just giving an example work, and I want to inspire you and hope there's more work can bring like causality and other machine learning direction together. So in machine learning, there is a suffering from not robustness, right? So for MNIST, you train a network, you shift it a little bit, then the performance is really bad. Or there's adversary attack. You just add some noise to image, then the classification is completely wrong for regular deep learning models. And then, but humans are very robust, right? So one of the reasons is we actually can separate what we see here may be caused by these independent mechanisms, or this is modular property from causality. Like if we see a digit 7, but how it appears, it may be caused of it's a 7, there are writing style, but there may be interventions like inject noise, we rotate it, and all these things. So we're robust to it because we understand the underlying causal process and generating process. But for machine learning, if they fit this model data directly, they don't understand it. And if you just shift something that they've never seen before, they become not robust. The same for other scenario, other type of data. So if we know the causal relationship, we actually can build a machine learning model that is consistent with your causal. So this is a causal like relationship. This means y is a cause of x. And then, you know, like for deep generative model, it's a generative model, it's deep learning. All this, if you only look at here, it's just a variation autoencoder. So you can actually build a deep generative model that is fully causal consistent. And in this way, so this is a simple setting that is the same as this MNIST image. And you can have many variables, like as we talked before. And if you actually have prediction target, you only care about the Markov blanket of it. So you can build any deep generative model that is consistent with the causal relationship you actually know. So what we show here is if you build a deep generative model that is consistent to causal relationship, that is significantly more robust. So these are two popular gradient-based attack. And you can see this is neural network. I mean, this is MNIST. We all get almost a perfect classification when the data is clean. And then if more with this is epsilon, with how much you can move, how much noise you can add, this is regular deep neural network. And then it's quickly, the performance drops very bad. And this is like the two kind of different variants of our method. You can see that these are two different settings. We are much more robust than regular neural network just because we consider the causal relationship. And this is the same on the more generic data. The previous one was MNIST. This is on simulated data with many variables. So we can see that with causality, we can also use our learning from causality, bridge the gap to other machine learning direction, to deep learning, deep generative model, robustness, and then to improve the performance of that. So I think that ends my talk. So I briefly talk about the methodology, which have the 3 methods for causal discovery, and also talk about our work on how to deal with missing data. I introduce a evaluation data set, how we can actually collaborate with different domain expert and create more evaluation methods for causal discovery. And in the end, I gave an example of how our knowledge from causal discovery can help other machine learning direction as well. So these are all examples, and I hope that it can inspire you to get interested in this direction and have more fantastic work contributing to all these directions. So I think I'm exactly on time. I don't know, Javier, how should we arrange it? Should next talk start, or should I stay a little bit for answer other questions?
Hi, Chen. I think Javier is having a problem with his computer. Okay. So I don't see Dominic yet connected. So maybe if you want to, maybe 2 questions or so, if that's fine with you.
Okay, sure.
Great. There is the last question there. Can you see, Chen?
Yeah, I can see. Can your method also used to inform? So can your method also be used to inform if there isn't enough data rather than missing data, or there is noise in some proportion of the data set, both of which can come in the way of accurate causal discovery? So if you're talking about the missing value PC, no, we cannot be used to inform if there's enough data. This is just for other part. I mean, without missing data value, we cannot do that by default, because that was not designed for it. You can think about things, I'm just dumping things from my mind, for example. Like there are different heuristics that you can think about, because that's also a problem in causal discovery. Like if you use different subsets of data, whether you still got a consistent result. Maybe you subsample half of your data, you output a causal graph, and you subsample another 50% of data and output another causal graph. Does this have the same conclusion, right? So in this way, I think it can tell you something, but methods to really think about whether there's enough data or whether there's noisiness in the data in the causal setting, I think that will be extremely useful. And I think that's interesting research idea and the questions. Meanwhile, orthogonal to it, I think just even outside of causality, in the content of data, I think if you also in Europe have a new workshop is data curation. So I think sometimes the noisiness of the data is something not only in causality, but generic across all different machine learning field, right? And there are in some method you can get inspired from other machine learning field. For example, there are methods setting temperature and learn a temperature of single data point. You can think about each single data point, they have different noise level, they carry different amount of information. One of the work, I think I know work from Stefan Ment is variational tempering. Similar work was in David Blythe's group, think about how to reweighting noisy data and other consideration. But there's also quite a bit debate on how do you define noise, or this is the data really, really valuable, but very rare, right? So these are all open questions. I see Dominic is here now. So I think I'll stop here and hope I answered your question.
Thank you, Shem, for the talk. And yeah, I think we're gonna make the slides available for people on the website.
Okay.
Yeah. So hope to see you at the discussion.
Thank you.
Thanks. So hello, Dominic. I think Javier was supposed to share your.
Hello. Hello.
Hello.
So, I just start screen sharing.